Back in September of 2019, I made a video where I attempted to derive the Euler Lagrange equation from a non-protuberance argument. I think I was a bit overambitious and delivered work that was quite sloppy as a result. I was trying to force a square peg into a round hole because I was so sure that geodesics and the Euler Lagrange equation are related in some way. That video wasn't verified as thoroughly as it should have been and had notation issues to say the least. But it's a very difficult topic, at least for me, and it's very easy to screw up and think that you're doing something right when you're not. So I thought I'd just upload some new thoughts I've had and simply hope that it doesn't dig the hole of misunderstanding even deeper than it already was and may actually slightly redeem me. I flat out don't have a clue what I'm doing, but I want to try to do something anyway. I could very well be repeating the mistakes of illegitimate sloppy math again. Suppose I draw a straight line like this one here. Now the big thing about 2D surfaces in general is that the basis vectors at each point can vary. I spoke about this in my video on geodesics, and I'm pretty sure I didn't make any major errors in that one because it matches up with legitimate books so well. Well, for the line to stay straight on a surface with varying basis vectors, I would imagine that the line goes in the same proportion horizontally as it does vertically at every single point. For this to happen, every time the tiny basis vectors along the path change, they have to change proportionally for our line to stay straight. Here, on the left side of the screen, we see visually the tiny changes in the tiny basis vectors. And on the right side of the screen, we see an equation setting the proportion of these tiny changes equal to the proportion of the infinitesimal, quote-unquote, length of the tiny basis vectors. Now that the equation is set up, let's focus on manipulating the left and right sides of the equation. First, the right side because it's easier. Well, we've got a differential fraction divided by a differential fraction here. I know with finite fraction division, you can just flip the denominator and multiply to get the answer. Whether it works with these kind of differentials, I don't know, but I think it's valid in this case. We do something similar to the left side. Now we can rewrite the equation with a lot fewer dx's in it. The blue equation on the right still looks complicated, but there are quite a few less terms. The left side of this blue equation is what looks complicated in particular, but it might be the notation in the parentheses that are somewhat misleading. Without doing any algebraic manipulation whatsoever, taking a closer look, we see in this expression that we're just taking two different derivatives of EY. First in terms of dx, and then in terms of dex of dx. Now, if EY is a function of x and dex over dx, we can take the derivative of it in terms of either one of these variables. And I'd like to imagine that there's a situation where the order we take these derivatives doesn't matter. Maybe if x and dex over dx are independent, or something like that. I know when you first learn partial derivatives, they're independent. I just haven't looked up any proofs to see if taking the order of partial derivatives matters. I think the most I did was type the question in Google. Not good research, but I get tired. Well, if changing the order of derivatives doesn't matter, we'll change the order for the heck of it. Now, we rewrote the blue equation by simply looking more closely at the notation and changing the order of the differentiation. Well, big deal. So what? Well, I'm going to once again try to force a square peg into a round hole and say that EY equals L, EX equals F, and DX equals DT. If we make those substitutions, it sure looks like the Euler Lagrange equation to me. I've never had a chance to really look at a book on Lagrangian mechanics, or even really grasp the concepts behind it, so I have no clue if this last step I did has any merit or even any real-world representation behind it that explains it. So why I felt like exploring this mathematical relationship that I really have a lot of confusion about to make a video that might be full of flaws and that nobody will ever watch, I have no idea. It kind of makes me feel like Joe from the movie Skydivers. A stranger comes to town, touches nobody's life, and then leaves. Still hilarious to me.